So far, much of what we've done has been to analyze problems where there have been no volumetric generation effects. And by volumetric generation, we mean any kind of energy transfer or energy generation that occurs within the volume of the material. And this is perhaps a little abstract, so let's talk about a practical example of this. So one of the problems that I've worked on and I work and in terms of research is fire. And in fire, one of the main causes of fire is caused by electrical overheating in terms of wires, extension cords, etc. And one of the ways that this can be modeled is that there's a conductor. So this is our copper conductor that's carrying current, and it's, typically these are adjacent copper strands. So let's just be clear on that. So we have adjacent copper strands that are both insulated. So there's some material that sheets these and protects and insulates them both between the conductors and between the conductors and the exterior. Now, as you know, the fact that there's a current being carried through here means that there's a Joule heating process that's occurring within the material. So let's just, so there's a Joule heating process that occurs inside the material itself, inside the copper conductor. And the power, or the total heat transfer rate that's occurring, the total generation rate within a length of wire is going to be equal to the voltage times the current. So for the length of wire, if this is happening uniformly, then we can talk about a volumetric generation rate. So this VI has units of watts. So this would be equal to, divided by, I'm going to use the simple V for the volume. So it would be voltage current over, and for a particular strand of wire, it'd be, for example, the cross-sectional area times the length. Okay, so within any amount of wire, there's going to be a volumetric generation process occurring. And it says that in some infinitesimally small strand of this wire, and we'll say it's, some cross-section or some radial variation in it, that there is that amount of heating per any volume, whether it's a differential volume, whether it's a full volume in the system. Now, the reason we were interested in this problem from a fire perspective is as you overload these systems, not surprisingly, you get increasing heating and you get accelerated degradation, accelerated aging of the insulator. So these are polymer systems, and with these polymer systems, there's an Arrhenius or exponential variation in the life reduction of this system in terms of its overall degradation as a function of its temperature. So each of these sheaths is rated for a different temperature. So you have different temperature insulating systems. As you expose them to higher temperatures because of overcurrent or over voltage within the conductors, within the wires, you start to degrade these systems. And as you degrade them, when you start to bend and fold them, you actually can completely fail them. And as you fail them, and there's less and less of these things available, you can get an arcing process, and that arcing process would lead to a fire. So from our purposes, we want to understand and analyze the simple issues of Joule heating or any kind of other volumetric generation within materials. And we're going to use the cylindrical system as an example. So The idea here is that there's a solid material of some perhaps very large relative to what we've shown here radius, and we're only looking at some element of extent delta r. So we're looking at a shell of delta r thickness for this material, for this solid. And we're going to do the same energy transfer processes that we've looked at before. We say that there's a certain amount of heat that passes through at the r length, and we know that there's a certain amount of heat that passes through at r plus delta r. Excuse me here, I don't know why I'm using capital R here. So again, r plus delta r. And we're going to perform an energy balance on this section. And for this energy balance, the way I want you to think about this is this. I want you to think that energy in minus energy out is equal to the rate of storage of energy minus the amount of energy that's generated. So in minus out is equal to storage minus generation. So let's think about if that makes sense. If there were no out, no generation, then in has to equal storage. If there were no in and no storage, then generation has to equal what goes out. Does that make sense? Okay, so in minus out is equal to storage minus generation. Let's just, again, write that out. In minus out is equal to storage minus generation. So that's the rule that we're going to be using in terms of analyzing this problem. There is no storage because this is a steady state problem. So we assume this is happening for a long time. There are no changes in the temperature at any point with respect to time. So coming into this control volume of delta R thickness is a Q dot R, so this is in. And going out is a QR plus delta R. And we are taking the generation to the other side of this equal sign, and this is the generation. So this is the volumetric generation. Times the volume of this shell, which is the perimeter times the thickness times the length. Okay, so it's perimeter P thickness delta R length L. So that's what this represents. So we divide by delta R. And so the delta R here goes underneath the heat transfer rate terms. We do this limiting process as delta R goes to 0. This is the definition of a derivative in the limit. And I'm using, so I've been using sort of interchangeably Q is equal to Q dot, so this is just the heat transfer rate. We're going to show, of course, that this is going to be equal to a Ka dt dr by Fourier's law. And so we go to the next step, which is, again, this understanding of what Fourier's law for this process is. So Q dot is AQ double prime. So this is the flux term. This is the total transfer rate. as compared to the watts per meter squared term. This is our area of transfer. So think about this. The area that this Q prime crosses is the perimeter, this 2 pi r, times the overall length of this section, which is this L into the board. And of course, this is our definition of Fourier's law. So the differential equation that we need to solve to get the temperature distribution, maximum temperature, etc., is shown to the left of what I was just writing. And again, it's a second-order linear differential equation. So we finally have a source term. It's a simple source term. It's a constant. We're not looking at anything crazy immediately. And of course, there are many possible boundary conditions that we could look at, including the fact, and this is sort of more typical in a conductor suspended in some reservoir fluid like air, that there's a heat transfer coefficient. We'll later learn in convection. This is a natural convection heat transfer coefficient that interacts with a stream at, say, temperature T1. And oftentimes we're trying to understand what that maximum temperature of the conductor will be. I think you'll agree with me that for a volumetric source, a constant volumetric source, the maximum is going to be at the center. So for sufficiently high heat transfer rate, and we'll talk about this later, it means that high heat flux, high heat transfer coefficient, let's say high heat transfer coefficient, it means that the surface temperature is equal to the free stream temperature, or is equal to the reservoir temperature. So that's an important approximation that's used in heat transfer systems. So here we have one Dirichlet condition because of this approximation. Here we have, for the other boundary condition, we have a Neumann condition, and it's a particular Neumann condition, which is either, you can call it an adiabatic condition. For this system, it probably makes more sense to call it a symmetry condition. And what it means is this. As you look, so for cylindrical and spherical solids, as you think about what the temperature distribution looks like, there has to be some sort of symmetry around the center. And so if there is symmetry around the center, it means that the amount of heat that's transferred in one direction is the same as the amount of heat that's transferred in the other direction, and that eventually you have a zero heat transfer rate condition at the center. So dT/dr is equal to 0 at this sort of symmetry point. Okay, you can think about it as a maximum or a minimum also. So it's got to be a maximum or minimum. Remember, I think some time ago we discussed that. So in terms of the differential equation, it's just straightforward integration. So it's a series of integrations that we're doing. So after integrating one time, we have this relationship. And dividing through by R. This R, if you recall, is part of the perimeter. And that perimeter specification is because of the area that we were using for the problem. And so by applying the R is equal to 0 condition, so you see that this thing, which is that constant of integration divided by R, has a problem at R is equal to 0. We know that dT/dr has to be equal to 0 at 0, and we'd have a C1 over 0, so the only thing that can happen here is it says that C1 has to be equal to 0. So we integrate again. So we've lost C1 by symmetry boundary condition. We need to figure out what C2 is. We apply our second condition, which is the external condition, so the external boundary, or that Dirichlet condition. And so we're essentially done. So we identify what C2 is in terms of T1, and so T1 is known here, and the volumetric source. We substitute C2 into the original equation. And we're done as far as our temperature distribution is concerned. There are many different ways to identify where the maximum is, but intuition tells us it's got to be at R is equal to 0. And we identify what the maximum temperature is for this system. Okay.